Hello friends, I welcome you in lecture number 42 on Laplace transform. In this lecture also we will discuss one question on finding inverse Laplace transform of given function using convolution theorem. So this question was asked in GTU Summer 2010 exam. Question is state convolution theorem and using it find inverse Laplace transform of this function a divided by s square times s square plus a square, and here a is considered as constant. So first you have to write down the statement of convolution theorem, and we have already discussed what is convolution theorem, but we just write it for recall of convolution theorem. So convolution theorem says that if inverse Laplace transform of capital F of s is equal to small f of t, and inverse Laplace transform of capital G of s equal to small g of t, then inverse Laplace transform of the product of capital F and capital G is given by convolution of this small f and small g, that is f star g of t. And we know the definition of convolution. It is equal to integral from 0 to t f of u g of t minus u du, and we know that f star g and g star f are equal, so we can use any function as capital F and any other function as capital G. So that is our choice, which function we will consider as capital F and capital G is also our choice. So here given function is a divided by s square times s square plus a square. So we first rewrite this function as the product of two functions. So we consider one function as a divided by s square plus a square, and another function is 1 divided by s square. So I split this into two parts, a divided by s square plus a square into 1 divided by s square, and I will consider this first function as capital F of s and second function as capital G of s. So we mention that where capital F of s is taken as a divided by s square plus a square, and capital G of s is considered as 1 divided by s square. Now to use this result, we first require inverse Laplace transform of capital F and capital G. So next step is to write down the inverse Laplace transforms of capital F and capital G. Inverse Laplace transform of a divided by s square plus a square is sin at, and this we considered as small f of t. Similarly, inverse Laplace transform of capital G is equal to inverse Laplace transform of 1 by s square, and it is nothing but t, and this we consider as g of t. So f of t is sin at, g of t equal to t. And now once we have these two functions, small f and small g, we can write the convolution theorem to obtain the inverse Laplace transform of f of s into g of s. By convolution theorem, inverse Laplace transform of capital F into capital G equal to convolution of small f and small g, and by the definition of convolution, this is integral from 0 to t f of u g of t minus u integral with respect to u. F of t is sin at, therefore f of u is sin au. and g of t is t, therefore g of t minus u is t minus u. From this we obtain f of u. F of t is sin 80, therefore f of u is sin au. G of t equal to t, and we require g of t minus u, so here we replace t by t minus u. Now we have to integrate this, and we keep in mind that integral is with respect to u, so we have to consider t as constant, and we can apply integration by parts. So for that we consider t minus u as first function, t minus u as it is. Integral of sin au with respect to u is minus cos a into u divided by coefficient of u, which is a, minus derivative of this first bracket with respect to u, so that is going to be 0 minus 1. Derivative of minus u with respect to u is minus 1. Derivative of t is 0 because t is constant when we integrate with respect to u. So derivative of t minus u with respect to u is minus 1, and in the product we have to consider integral of this function minus cos au divided by a. Integral of this cos au is sin au divided by a, and there is already minus 1 by a in the product, therefore integral of this bracket will be equal to negative of sin au divided by a square. And in the next term we have to write derivative of minus 1, and it is 0, therefore integration by parts stops here. We will have only these two terms because all the derivatives after this will be equal to 0. So again we repeat, we know the formula for integration by parts. It is equal to integral of u into v is equal to u as it is integral of v, then derivative of u into integral of v1, which is denoted by v2, and so on. Here instead of u we consider t minus u, so t minus u as it is, and v is considered as sin au. T minus u as it is, integral of sin au is minus cos au divided by a. Minus comes from the formula, then we have to write derivative of first bracket with respect to u, which is minus 1, and integral of this second bracket. Now minus 1 by a is constant, and integral of cos au is sin au divided by a, therefore we have minus sin au divided by a square. Now we have to simply put limits of u. First we put u equal to t, and then we put u equal to 0. So if we put u equal to t, here we will have u minus u, that is 0. So this term will become 0 when we put u equal to t. And here we have 3 negative signs. So this is going to be positive, and we have already negative sign inside the bracket, and we substitute u equal to t. So we have sin at divided by a square with negative sign. This is for u equal to t, that is for upper limit. Minus, now we write for u equal to 0. So when we take u equal to 0, here we will have t minus 0, that is there will be t here only. If we take u equal to 0, t minus u will be equal to t. When we put u equal to 0, we will have cos 0 here, that is going to be 1, and minus 1 by a will be there. So we have minus t divided by a. This is going to be t for u equal to 0, and this bracket will be minus 1 by a for u equal to 0. So we have minus t divided by a, and here we will have sin 0, and sin 0 is 0. So this term will be equal to 0 for u equal to 0. So finally we have minus sin at divided by a square, and negative negative positive, t divided by a, and if we wish we can take LCM as a square. So here I have to multiply by a, so a into t minus sin at divided by a square. So, and the left hand side was we have obtained inverse Laplace transform of f of s into g of s, and the product of these two is nothing but a divided by s square into s square plus a square. So finally we have obtained the inverse Laplace transform of given function, which is a divided by s square times s square plus a square. So what we have done here, we have written our function as product of two functions, a divided by s square times s square plus a square. This we write as a divided by s square plus a square into 1 by s square. This we call as capital F, this we call as capital G, and then we obtain inverse Laplace transform of these two functions. Here it is sin at, here it is t. This we consider as small f, this we consider as small g, and inverse Laplace transform of this function is nothing but convolution of these two functions by the convolution theorem. So we can easily obtain inverse Laplace transform of some functions using convolution theorem easily. We can find out the inverse Laplace transform of this function by another method also, like we can find out the inverse Laplace transform using method of partial fractions, as well as we can use the method of division by s that we have discussed in some of the previous lectures. So there are two other methods for doing the inverse Laplace transform of this function, but here it is specified that using convolution theorem obtain the inverse Laplace transform. So you have to write your answer using convolution theorem only. If it is not specified, suppose they ask you to obtain inverse Laplace transform of this function only, then you can use any of these three methods to obtain the inverse Laplace transform of these functions. Those three methods are method of partial fractions, division by s, and convolution theorem. So we can do the same problem using different methods, and our answers must be same whatever method we apply. And if some method is specified, then we must use specified method only. If nothing is specified, then we can use the method in which we are comfortable. So this is all about this session. I hope you like it. Thank you very much.